Hi, good morning, everyone. This is Dr. Sharif El-Gamal again with you, and today I'm going to talk to you about an important topic in reinforced concrete design, which will be foundation design. Please don't forget to subscribe and turn on notification to receive all new videos. As you know, loads are transferred from slabs or beams to the columns. Columns will take the load to the foundation, and the foundation will take it to the soil. So in this video, I'm going to talk with you about how to design these foundations. There are different types of foundations. We can classify them into two main types: shallow foundation and deep foundation. For shallow foundations, you can see that the footing or the foundation will be resting on the soil at shallow level. If this is the soil level, so it will be close from the soil level, and we use this when we have soil with good bearing capacity. Let's say if you have a soil here which is the bearing capacity is very low, or you have very high loads from the building, so the soil at this level cannot resist loads from the building. So what will be the solution in this case? We have to go to the deep foundation, where we can use like piles, for example, to transfer load from the weak soil close to the surface to a deeper level of soil with higher bearing capacity. So in this case, the building or the soil will be able to resist the load from the building. In this video, I will concentrate about shallow foundation. And in shallow foundations, we have many types of shallow foundations, starting from pad footings. And pad footing or isolated footing, when you have one column supported on one footing. So we have a footing supporting only one column. We call this type of footing as pad footings. Combined footing here, when you have two footings, if you have two footings, pad footings are overlapping with each other, they are close for each other, and in this case they will overlap, so we can combine them to make one footing that supports two columns, as you can see here. If you have more than two columns, 3, 4, 5 columns or more at like one line, as you can see here, we can make also one footing that will be supporting all of these columns, and we call these footings as strip footings. In case if you have many of the footings in your building are overlapping with each other, so it will be in this case more economical to use raft foundation, especially if you have higher loads and you have many overlaps between the footings. So in this case, we go to the option of making mat or raft foundation. Okay, in this video I will be talking about pad footings, and in coming videos we'll be talking about other types of footings. For pad footings, we have, it could be square or it could be rectangular. Usually if you have a square column, we use a square footing. Also if you have a circular column, also we can use a square footing. And if you have a rectangular column, so we can use either square footing or also we use a rectangular footing, as you can see here in this figure. How about loading and footing? For calculating the area of the footing, we use loads as serviceability limit states. Okay, as you know, we have two types of loadings. We have loads at service limit states, and we have loads at ultimate limit states. Of course, the ultimate loads equal the service load multiplied by some load factors. So to get the area of the footing, okay, we use the load at the service limit state without multiplying this load by any load factors. Okay, what are these loads? We can get them from different load combinations. It could be only dead load plus live load, or if we use dead plus wind load, so it will be dead load plus wind load. If we have a combination of dead, live, and wind load, so we can use this combination. This is according to the BS code. If you are using any other code, you will use a combination from that code. The bearing pressure under the base area of the foundation shouldn't exceed the safe or allowable bearing pressure of the soil. Okay, each type of soil has its allowable bearing pressure. And when we design the footing, we should use an area of the footing that will not result in exceeding this safe or allowable bearing pressure of the soil. So what is this allowable bearing pressure of the soil? This is depends on the type of the soil. We can get these values using soil investigation, and from the soil investigation report, it will tell us how much is the bearing capacity of the soil, and at which level we can make our foundation, and many other information we can get it from the soil investigation report. As you can see from this table, it gives you like some typical allowable bearing values for different types of soils. You cannot use these values to make your design, as I just explained. To make a design for a specific building, you have to make a soil investigation, and based on the soil investigation, it will tell you exactly at which level you can make your foundation, and also what is the bearing or allowable bearing value of your specific soil. But this is just a guideline for different types, and you can see here, like for soft clay, it's a very weak soil. We can see that it is less than 75 kilonewton per meter square. Usually, these bearing values are given as kilonewton per meter square. What does this mean? It means if you have a meter square of footing, 1 meter by 1 meter, it will be able to carry a load of 75 kilonewton. And this increase as you have different types of soils, from medium clay, hard clay, loose and fine sand. You can go higher until getting very high values if you are using for some specific types of rocks. Okay. Usually for medium or dense sand, it is ranging from 100 to 300 kilonewton per meter square based on the density of the sand and the type of the soil. And you have to get this again from the soil investigation. We have some design considerations we should follow to make our design of footing. First of all, we have to assume linear distribution of soil pressure under the base of the footing. Let's say you have a footing like this, and if you have a load here, so this will be the pressure, and you can see it is uniform pressure because we have only axial load, okay? But if you have an axial load and some bending moment, again, we will assume also linear distribution, but of course, you will have higher pressure here compared to the other side. But again, we assume linear distribution of soil pressure. Of course, in reality, sometimes you may have non-linear distribution. It could be higher under the column or higher at the edges, depends on many parameters. But just to facilitate our design, the code here is assuming that we will assume only linear distribution. It could be uniform, it could be linear with higher value at one side and lower value at the other side. We will not assume non-linear distribution of soil pressure because it will make it very complicated in the design of reinforcement and check for shear and punching shear. Also here, a large cover should be used. It is not similar to the slabs or beams or columns. Here, the foundations are inside the soil, which is aggressive and severe exposure. So in this case, we have to use bigger cover, larger cover to protect the steel reinforcement against corrosion and chloride attack. So if we are using the reinforced concrete footing directly on the soil, okay, without any blinding concrete, so the minimum cover will be 75 millimeter according to the BS code. And if we are using a blinding concrete here, a small layer of plain concrete to protect the reinforced concrete footing, in this case, the code is allowing us to reduce the cover, but again, it cannot be less than 50 millimeters. So the minimum cover for the footing when you are using a blinding concrete will be 50 millimeters. Without blinding concrete, we cannot go less than 75 millimeters. These are the minimum. You can increase them. Of course, you can increase them. Okay. Also, the grade of the concrete, we should use 35 Newton per millimeter square at least. Okay, so the grade of the concrete should be at least 35 megapascal or higher. Again, because you need a good quality concrete to protect the steel reinforcement against corrosion and chloride attack and chemical attacks. Okay, so 75 without blinding concrete, 50 with blinding concrete, and the minimum here for the concrete strength is 35 megapascal. Okay, what will be the pressure distribution in the soil? If we have here, assume a rectangular footing with a short side of B capital and long side of D capital, and the depth of the footing, the total depth, it will be assumed as an H. Okay, if we have a column here on the footing, so we will have two different cases. First case, if you have only axial load on the footing, like in kilonewton, only axial load exactly at the middle of the footing. So in this case, we will have a uniform pressure. It will be a uniform pressure. How much it will be this value? Pressure or stress equals force divided by area. So the stress here, which we call it P, soil pressure, equals this force divided by the area of the footing. So it will be N divided by B times D. N divided by B times D, N over area. The second case, when you have an axial force plus moment. Okay, so there is some eccentricity. This can come from moment and normal force, or if you have only normal force, but the column is not exactly at the center line of the footing, so it will result also in a moment in this case. So in this case, you will have a linear distribution with two values, higher value here, because the moment is pushing in this side, so it will result in higher pressure in this right side and lower pressure in the other side. How to get these two values? We can get them from the famous equation that N over A from the axial load plus or minus M over I times Y. Okay, the moment divided by the I times Y. What is this I? This is the inertia of the footing here in the direction of moment, so it will be about this axis. As you know, it will be B times D cube over 12 because this is a rectangular cross section, so the inertia will be B times D cube over 12. And what is Y here is the distance from the center line here to the edge, which is D over 2. So if you substitute here, Y equals D over 2 and I equals B times D cube over 12, in this equation, you will find that M over I times Y equals 6M over B D squared. So P1 here, it will be minus because the moment is reducing the pressure. Okay. However, for B2, it will be exactly the same, but instead of minus, we will use plus. So it will be N over BD plus 6M over BD squared. We need these values if you have some moment and normal force, or only if you have a normal force, but the column is not exactly at the center line of the footing. So in this case, again, it will result in some moment, and we have to use this equation to get the stresses left and right. We have different types of these stresses, or like we can classify them into 3 stages. But before doing that, we will have a new term here, which is called eccentricity. When you have normal force or axial force and moment. So in this case, we will have something called eccentricity. The eccentricity equals the ratio between the moment and the axial force. Okay, so based on this value E, which depends on M and N, we will have 3 different types. First of all, if E is less than D over 6, where D is this distance here, this dimension of the footing in the same direction of the moment. If the eccentricity is less than D over 6, we will have this distribution. Both sides will be under compression, but we have higher compression here and lower compression in this side. If the E equals exactly D over 6, okay, equals D over 6, so in this case, we will have this triangle distribution. You have a maximum value here, and you will have a 0 stress at the other side of the footing. If you increase, this E is greater than D over 6, so now we'll start seeing some tension force because the eccentricity is big. So you have a bigger value here, but it will result in some tension force at this left side of the footing. This is not recommended to have a footing with some tension here because, as you know, soil is weak to resist the tension. So if you have this case, the part in tension is ignored in the design. So if you are forced to design a footing with this case here, so you have to consider only this part, and you should be sure that the stress here will not exceed the allowable bearing pressure of the soil. But if it is possible, never take E greater than D over 6 to not have tension on the soil. In some cases, you have no choice, especially if you have a column at an edge of a footing. Okay, so in this case, there is a solution. Yes, of course, there is a solution. We can use tie beam to connect the two columns. If you have a column here with big eccentricity, for example, okay, and you will have tension on the soil, or the soil will not be able to resist this linear or like higher stresses here. So what is the solution? In this case, we can use a big beam here, we call it tie beam, to connect this footing with an adjacent footing here, so the distribution of the soil pressure will be better in this case, because we connected this column with another column here. And usually this is a big beam with a lot of reinforcement. We will go through a video about this in a separate video in the future. Okay, so we use this tie beam to connect two columns to make the distribution, soil distribution is in a better shape. How to design for a footing? We have to design for reinforcement, and then we have to check for two different types of shear. Let's start first by design for moment, or to get the reinforcement of the footing, we have to design for the moment. The critical section, okay, on for the moment will be exactly at the face of the column. Okay, so there is a critical section for moment. Yes, in bad footings, it will be at the face of the column here. So we will calculate the moment at the face of the column. How to calculate this moment here? We have first to calculate the soil pressure. P equals kilonewton per meter square. And this soil pressure, we will calculate it at the ultimate limit state. Okay, so for any calculation of moment or checking for shear, we have to calculate this P here at the ultimate limit state. So we'll use the N at the ultimate, not at the surface. Okay, so once you calculated P, and you know this will be the critical section, okay, we have now to calculate the moment due to this cantilever. Let's see how to do that. So let's say first we'll get the reinforcement in the long direction. If this is the long direction of the footing and the B is the short direction, we will get it first on the long direction, and then we repeat on the short direction. For the long direction here, again, this will be the critical section exactly at the face of the column. Okay, so to get the moment at this point here, we have to get this force. Okay, this F capital. How much is this force here? This force here equals the stress in kilonewton per meter square, P, times this area. A force equal stress times area. So kilonewton per meter square, this is the stress multiplied by area, which is meter square. This meter square will go with the meter square. So again, at the end, we will have this F will be as kilonewton. So F here will be the force coming from the soil pressure for this part here, or this area here. Okay, and the critical cross section, or the critical section for the moment, is exactly at the face of the column. Okay, so if you have this force F as kilonewton, can we calculate the moment? This is very easy. So the moment here will be F times L over 2. But what is this L first? What is this L? L here, you can calculate it easily. It equals D minus HC, width of the column here, divided by 2. So it is D minus HT. C, it will give you L here and another L divided by 2. It will give you only L in one side. If you know this L here, so you can get this F. F equals B times B capital here times L. Once you have this one, we can calculate the moment. The moment in this case equals F times lever arm here, which is L capital over 2. So the moment at the face of the column equals F times L over 2. Once you have the moment in kilonewton meters, this will be easy now to calculate the K equals M over FCU BD square. But keep in your mind that now we are getting the reinforcement here in the long direction for the whole width of the footing. Okay, so the B in this case, or the width of the cross section, it will be the whole width of the footing, which is B capital in this case. So K equals M over FCU B and D square, which is the depth here. Then once you calculate the K, calculate the Z, okay, equals D times 0.5 plus square root 0.25 minus K over 0.9, and according to the BS code, this should be less than or equals to 0.95D. Then calculate the AS required M over 0.95 F yield times Z. Of course, calculating the moment here until this step, every code is using the same. About calculating the reinforcement, based on which code you are using, you can calculate the area of the steel reinforcement. According to the BS code here, these are the equations. We calculate K, we calculate Z, and we calculate the AS required. And keep in mind that the AS required will be the whole reinforcement here in the long direction. Okay, so this area, it means the whole reinforcement in the long direction. You can use a suitable diameter, and based on the diameter, you can get the number of bars in the long direction. Once you did this in the long direction, you have to repeat this again in the short direction, and you get the reinforcement in the other direction using the same steps. Okay, after we calculate the reinforcement, we have to make two checks. Okay, the first one is check for direct shear, or sometimes you call it one-way shear. This one-way shear or direct shear, according to the BS code, is telling us that the critical section for direct shear is at a distance D from the face of the column. So for the moment section is exactly at the face, but for checking shear, direct shear or one-way shear, it is at a distance D from the face of the column. If this is the face of the column here, so this distance here is equals to D. So how to check for shear? We have to find first the shear force. Shear force, which is, we call it V here. This shear force, again, the force equals the stress times area, this hatched area here. So it will equal P times the area. P is kilonewton per meter square times area in meter square. Meter square will go with meter square, so the V here, it will be in kilonewton in this case. So how much is this area? It equals B times L. B times L here, and to find this L, again, this is easy. This L equals D minus HC all over 2 minus this D here. You will be able to find this distance L. Once you found the L, multiply L times B times P. It will give you the shear force as kilonewton. Once you have the shear force, you can now check the shear stress. Okay, so to get the shear stress, you divide the shear force by the shear area. In this case, the shear area, it will be the critical section at this point. You can see it here. This area equals B, the width of the footing here, times D. So the V stress, V small, equals V capital, the shear force divided by the cross section here, which is B times D. It will be Newton per millimeter square. You have to check this, that shear stress is less than the VC, or the shear carried by the concrete. And if it is less than the VC, it means your design or your first check for shear, one-way shear, is safe. If it is not safe, what is the solution? You have to increase the depth of the footing. You have to increase this H here to reach a safe shear stress on the footing. This is the first type of shear. We call it one-way shear. There is another important type of shear, which is punching shear check. We have to check for punching shear because you may have that because of the higher loads on the columns here. Sometimes this column can punch through the footing. So you have to check this one to be sure that the punching shear will be safe. What is the critical section for punching shear? According to the BS code, the British standard, it tells us that the critical section of the punching shear is at a distance 1.5 D from the face of the column. Okay, so from the face of the column, from each side here, you have a distance of 1.5 D, and this will be the critical section if a punching will occur in the footing. Okay, so again, the critical section for bending, it was exactly at the face of the column. The critical section for one-way shear, it at a distance D from the face of the column, but for the punching shear, it is at a distance 1.5 D from the face of the column. These values differ from one code to another. So if you are using another code, you have to check where is the critical section according to the code you are using to check for shear or punching shear. So how to get the shear force here or the punching shear force, V for punch, equals again any force equal stress times area. So the stress is the stress under the footing, P capital P equals kilonewton per meter square, multiplied by this hatched area here. Okay, so the idea here is to find this hatched area multiplied by the soil pressure. Okay, how to get this hatched area? Again, it is easy. It equals to the whole area of the footing, B capital times D capital times this punched area, this area here. And to get the punched area, this is again not difficult. If you know that 1.5D here and you have 1.5D here, and this is the H of the column, so the total distance from here to here equals 3D plus HC. And from the other side equals again 1.5D plus 1.5D, it is 3D plus B of the column. So if you know this dimension and this dimension, multiplying this distance by this distance, you can get the punched area. So the hatched area equals B capitals times D minus hatched area, which is 3D plus HC times 3D plus BC. Once you did that, you will be able to get the V punch, the punching shear force. Once we have the punching shear force, we can get the punching shear stress. Punching shear stress equals force divided by the area, or the area where we have the critical shear or punching shear. This area equals what? Equals this perimeter here, this distance, okay, times the depth of the footing. Okay, so the critical section here where we will have a punch, it will be through this perimeter of the punched area multiplied by this depth. So this V capital punch divided by this area equals D times this perimeter here, which is 3D plus H times 2 plus 3D plus BC times 2. So it will be this distance times 2, because we have from top and from bottom, and this distance here times 2 because you have it from left and right. So V small punching shear stress equals V capital punching shear force divided by D times twice 3D plus HC plus 3D plus BC. Once we did that, you can get the punching stress in Newton per millimeter square. And again, we have to compare this punching stress with the VC, or the shear stress carried by the concrete, and should be less than VC to have a punching, the punching shear safe in this case. If it is greater again than VC, you have to increase the depth of the foundation until you have a safe punching shear stress. Of course, you can use some shear reinforcement. Yes, you can use shear reinforcement, but will be like expensive to add shear reinforcement in the footing. You have another option also to increase the size of the column. Yes, you can increase the size of the column. Okay, you have many options, but the easiest one to increase the depth of the footing until you have a punching shear safe and also a direct shear safe. What are the design steps? Let's conclude the design steps of bad footings. First of all, we have to assume suitable value of the thickness. We have to assume a suitable value of the H of the footing, and based on this H, we will have the effective depth. As a guide to help you to calculate the H here, we can assume that the shear stress at the face of the column will be 0.5 V ultimate. 0.5 the ultimate shear stress in Newton per millimeter square. According to the BS code, the V ultimate equals the minimum of two values, 5 Newton per millimeter square or 0.8 square root of FCU. So this is only like a guideline to help you to get an initial H of the footing or a depth of the footing. So once we assume that, we can calculate the depth of the footing equals N ultimate. Okay, again, this is the ultimate force coming from the column divided by the column perimeter times 0.5 V ultimate, which we assumed it here. Once you use this equation here, you can get the D. Once you have the D, you can add the cover plus the diameter of the bars to get the total H of the footing. As a guide here, the H, we can assume it as 20 millimeter for the diameter of the reinforcement in the footing. So you have the H. Okay, what will be the second step? You have to round this edge up to the nearest 50 millimeters. So don't use like a footing of like 515 centimeter or 515 millimeter, sorry. No, because this is not practical. So you can use like 550, 600, 650, 700, and so on. Okay, and also what will be the minimum thickness of the footing? The H minimum is 300 millimeters. So don't use a footing of less than 300 millimeters because it will be very the thickness will be very small in this case and it will not work fine. So the minimum edge of the footing is 300 millimeter. Then you can increase by 50 millimeter, 350, 400, 450, and so on. Okay. Once we know this edge, we can go to the next step about calculating the area. But again, I'm concentrating here about N here at this first step. To calculate the edge, we use the N ultimate as the ultimate design load, ultimate limit state. So it equals the N service multiplied by the load factors. Okay. The second step, once you have the H here, you can calculate the plan size of the footing, the B capital and D capital. How to do that? We use the load at the serviceability limit state, not at the ultimate, okay? And we use the bearing pressure of the soil. So if you divide the load in the service limit state divided by the bearing pressure of the soil, okay? And in this case, you will be able, it will help you to find the B and D. And don't forget here, you may have different types of loading. It could be only axial load or it could be axial load and bending moments. So you have to use the load arrangement, the critical load arrangement based on loading on your footing that you are designing. Okay, so we first calculate the H at the ultimate using the ultimate design load. Then we will move again from the ultimate design load to the service load to calculate the B and D. So don't get confused here. For the H, we use the ultimate. However, for the D, we use the load as a service limit state and allowable bearing pressure of the soil. Okay, once you calculated the H and the other dimension of the footings and you check that the bearing or the stress under the footing will be less than the allowable bearing pressure, so it means it's okay. You can move to the next step at calculating the bearing pressure under the soil at the ultimate limit state. Okay, we have to calculate it at the ultimate limit state because we are going now to use it to make our design for reinforcement and also for checking for direct shear and punching shear. So once we calculated the stress under the soil at the ultimate limit state, we will use it as we explained a few minutes ago to design for reinforcement in the both directions, short direction and long directions. Then we have to check the direct shear stresses at the critical section of direct shear, which is at a distance 1D from the face of the column, where D is the effective depth of the footing. Then you have to check for punching shear at a distance 1.5D from the face of the column, as we explained earlier. Then we have to draw a plan and a section to show dimensions and reinforcement. Usually, this is showing a typical dimensions and reinforcement of a footing. You show an elevation of the footing, showing the D, showing the H, and the reinforcement here in the long direction and also in the short direction will be these circles here. This is the reinforcement of the column. You just can put it as an indication without telling how much is this value. Also, you draw a plan of the footing showing the dimensions of the footing here, B and D, and showing the reinforcement as lines here in the long direction and also in the short direction. Some detailing about reinforcement in the footing. First, the footing should be reinforcement in 2 layers. This bad footing should be 2 layers, both of them at the bottom side of the footing. Okay, each layer resists the moment in its direction. Like in this case, we will have 1 layer in the long direction or in the X direction. It will be this line here, and in this 3D, you will see it like this. This will be the reinforcement in 1 direction, and then we will have another layer of reinforcement directly above this bottom layer. In the other direction here, it will be like these circles here. So it is a mesh or a net of reinforcement. All of the reinforcement will be bottom because all the moment here or the tension here is in the bottom layer. Of course, if you have another type of foundation like combined footing, you will have two layers here, one layer in both direction at the bottom, and you will have another layer at the top. But this is in combined footing or strip footing or like raft foundation. Here, if we are talking about bat footing here, one column on only one footing, we need only bottom steel reinforcement because the tension is only at the bottom, no tension at the top. And you can see like X layer or horizontal layer and perpendicular layer. We usually say it in long direction and short direction. Of course, if you have a square footing, you will have exactly the same reinforcement in both directions. Okay, how about the depth here? Like, to make the things easier, we can assume that D here is constant value when we calculate for both layers. So it will be the average for both layers here. It means from the top or compression side until the middle here between the reinforcement in the short direction and in the long direction. So this will be the depth. No need to use a special depth for the bottom reinforcement and another depth for the top reinforcement. We can use only like one depth, average one for both layers. Okay, this will make it easier for you making your design. We can using a blinded concrete under the concrete, the reinforced concrete, or it can be like a PCC plain concrete footing under the reinforced concrete footing and can be considered in the design. If it is only a small layer, like it will be something called a blinding concrete, just to make it surface clean, to put the reinforcement using some spacer here to have the cover. Okay. The last thing here, that this distance from the critical moment section, which is at the face of the column, until the end of the steel reinforcement, should be at least equal to the anchorage length, full anchorage, full tension anchorage length behind this critical cross section. So this distance here should be at least about 40 times the bar diameter. If you have a bar diameter here, like let's say 20 millimeters, so at least will be 40 times the bar diameter, to be 800 millimeter. Okay, if this distance is not enough to cover or satisfy this 40 times the bar diameter, so we can use some bends here, we can use some hook, and you make some reinforcement with 90 degree and goes up to achieve this 40 times the bar diameter. So in some footings, you can see that only straight bars. In some other footing, you will be like bars with bends at both sides. Why we do that? To satisfy this requirement of full tension anchorage length from the face of the column. This is the end of our video today. This is part one. In the coming videos, we are going to talk about detailed design examples of footings with only axial load, and also another video about axial load and bending moment. Then we'll go to other types of footings. Thank you for watching. Please don't forget to subscribe, share, and turn on notification to receive new videos. Thank you, and see you in a coming video, and goodbye.